Hi there everyone, this is Shivani Patel. This is a webinar for common mistakes and tips for electronic devices in simulation. We're going to spend the first half of the webinar going over issues with FEA and the second half with issues in CFD. Let's get started. What I first want you to do when you're running an FEA is to run an interference detection. You're going to get that through the Evaluate tab, Interference Detection. When you hit Calculate, that's going to run it for every single component in the assembly, not by default the different parts in the multibody. Interfering parts are going to show up red on your screen. You can toggle through them through this box, and then you can always expand it and look at the parts individually. So what I recommend is having different configurations, and in those configurations, we need to simplify different part files. Perhaps get rid of small geometries or small holes, or get rid of components I don't actually need in the simulation. So that's what we've done here. We have this default configuration which has the legs on the microprocessors and the interferences. Instead of altering this one, which may have drawings associated with it, you can create your own new configuration like this FEA one, which doesn't have those small geometries and doesn't have the interferences. Now, if we wanted to not use those resistors, we're not forced to always do a new configuration with suppression. Another option is to use exclude components. We get that through the parts dropdown, and in the parts dropdown, you just shift select to grab a bunch of them, you right click and you go to exclude from analysis. So even though this will not affect our configuration in our overall assembly, it does make a change in this static study, or in this thermal study. The next thing we're going to take a look at is the heat power. So the heat power is one of our thermal inputs. Let's go ahead and copy all of our different materials into this study so we don't have to do that by hand. And then we'll add our thermal inputs. Let's do a heat power. The icon looks like it only applies to faces, edges, or points, but we can actually apply it to entire bodies. If you hover over it, you'll see that. However, if I try and click on the bodies on the screen, faces automatically get selected. So a quick tip here is to either go through the tree and select the bodies from this tree. Now, unfortunately, if it's a multi-body part, that becomes more annoying. You have to dig down a lot further. So I recommend hitting F5 on the keyboard. That brings up this selection toolbar, which will let you click the solid bodies selection filter and really easily click the components through there. Alright, so let's add it one more time, and this time to multiple components. Now let's think about how this gets divided. If I put this on total and put in a certain value, is this equally dividing by 2 for each one? In this case, the answer is yes, but what if their volumes were different? For example, if I included this component, it would not be divided by 3 for each one. Instead, the heat power would be relative to the size. So we're going to go ahead and leave it like this on total, let that divide by 2, and hit OK. Now let's go ahead and run this and see our first common mistake. And this time when we run it, we get some very oddball results. Looking at our legend, they're practically, let's say, infinite temperatures. They get extremely high. So what is going on here? We added heat to the system, but we did not give it a way to expel from the system. We forgot to add convection. Convection is not automatic in FEA thermal studies. What we got to do is right-click on our input conditions, go to convection, and click on all the faces that have airflow on. Now in this case, that's going to take a long time to try and click all those faces. So instead, we'll trick the system, or use a quick tip here. Just hit select all exposed faces, type in our value, and hit OK. Now when we run it, we're going to get more reasonable looking results. Okay, let's take a look at the next common mistake. And this time we're going to add another heat condition onto the other two integrated circuits. And in this case, we're going to turn on this temperature control. This allows it to change what kind of heat power it's applying depending on what temperature it reads on the circuit board. So we'll have this set up so that if it reads 0 degrees Fahrenheit, it'll run the full wattage, and then at 100 degrees Fahrenheit, it'll be completely off. So let's run this and see what happens. Remember how the colors look so we can compare this better? Okay, it just reran. Nothing looks different. Is that because it wasn't high enough temperature? No. We actually input the data in incorrectly. Look at it very closely. It says 0 here. If I go to edit definition, it says 0 here in this box too. If I hit view, my entire curve is 0. Now I know I didn't type in 0, so what the heck is going on here? Let's go to edit. Here the curve is slanted because that's the way I typed it in. Take a look at one of these columns. This column here is a multiplication factor. It's multiplying by whatever I've typed into this box here. So because it says 0, I'm just getting 0 watts out. What would make more sense in this case is to type in something like 0.1 or 0.2. Now my curve actually makes sense. Alright, we give this another run, and that's definitely made a difference. Alright, the next thing that I want to do is check out a transient analysis and see the errors here. I'll do a very low amount of seconds so that it runs fairly quickly. Alright, if I just try and run this to see how this changes over time, it immediately tells me, okay, I have to have some sort of initial condition. So you right click on heat inputs, you go to your temperature and you hit initial, and then you select all exposed faces, just like how we did with convection, right? Seems to work. We put in the temperature we want to start at. Something near room temperature sounds good. And let's give this another run. Distribution seems reasonable, but when we look at the numbers, they are very oddball. Looking at the low end of that scale, I've got some negative values. How the heck could that even be possible when I have an initial condition of room temperature and then only added heat to the system? Okay, so what's going on here is by default, the initial condition of all the bodies is 0 Kelvin. When we set initial condition of just the outside faces, we just put that on the outside faces. The interior volumes were still 0 Kelvin, which is what made these results so odd. So what you want to do instead is not do select all exposed faces, but instead use your select bodies filter. Box select will make it easier to grab everything, and then hit OK. That way their interior volumes are also set to that room temperature. Alright, looking much more reasonable. The next thing we want to do is take a look at a thermal stress test. In these ones, you can input your stress data using Properties, Flow Thermal Effects tab, and then import them from a particular study. Pick your time step here and hit OK. That's going to bring up the input into the external loads folder, and I just have to add a couple restraints. Alright, first error, we're missing some sort of material data. Let's take a look and figure out which one we're missing. It takes me to my FRH. Now what I'm missing here is this thermal expansion coefficient. If we take a look at these values, these letters, SOLIDWORKS is nice in that it color codes it for us. The reds are stuff you have to have. The blue is stuff that we recommend you have. What we're missing here is the thermal expansion coefficient. So we could go find it on a website, perhaps Materiality or MatWeb. Instead, I'll just use this one that we've pre-started and select it here. And actually, I want to mention something else. So when we're inputting these values for material data, we do know that this can change with temperature. So if this was getting very hot or very cold, these values would be changing. When that happens, we have this Tables and Curves tab near the top, which allows you to have those values change with temperature. Now here's where we get into the common mistake. Somebody comes in here and inputs all the data that they found online that they tested in their lab. Great. Then what they forget to do is come back here and tell it to link to the tables and curves. So you got to click on the box, hit the drop down, hit temperature dependent. That links it to whatever data you input. If you don't do that, it just stays constant. Alright, there we are with some pretty reasonable looking results. Alright, let's get into a couple things just in the results folder, some quick tips and some common problems. First one is section view. Everybody knows how to turn it on, not everybody knows how to turn it off. Button's in a weird spot. You gotta go back into section view, come down to the very bottom here. This button is the toggle to switch it on and off. Okay, the next thing I want to do is take a look at the stress on particular components. For example, this component carries a lot of the stress, but it's hidden by the heatsink. To take a look at a particular component, you right click on it, you go to isolate. Now when you do this, the screen doesn't update. This is one of those common little things that happens. The way I like to refresh the graphics is to either toggle deformed result, like so, or I right click on the plots and I go to hide and then show. Now we're going to do this again and isolate the PCB board. However, when we do this, a lot of other components comes with it. That's because this PCB board is part of a multi-body part file in which the heatsink and the other components are as well. This makes it much more complicated to isolate just the PCB. To get around it, I recommend using display states. Display states are like configurations but for graphics. You set them up in the same tab. I've already preset them here. I can go to my component properties and switch over to just showing the PCB. Save myself a lot of time, prevent myself from having to dig through the tree to just see the results on this PCB board. Now I could right click and isolate and I would just see the results here. Now if we go to edit definition and chart options, we have a checkbox for show min max on shown parts only. This changes the legend so that you get the whole color range on just the part showing on the screen. If other parts have max stresses, that doesn't count for the colors here. Alright, there's one more thing I want to mention, and it has to do with my units. As I've been setting up all these studies, it's kind of been perfect. Heat power was in the right units, Fahrenheit was exactly what I wanted. This is all because of my simulation options. I changed the units to match what I knew I am most commonly using. These are global settings, which means once you set them once, you don't have to set them again, and they will always show up for every new study that you create. Alright, now we're ready to check out the CFD portion. Let's start by adding a new project and walk through the settings here. Beginning with units, just like in FEA, we can customize these units as well to whatever we need in particular. Looking at the SI column, this is always comparing whatever value put in to the default SI. Even when you're making custom units, you have to relate these back to SI units, never to English units. Alright, this is going to be an external study. We have to do heat conduction in solids if we want conduction through our different materials. Now let's take a look at radiation. Depending on what package you have, you're going to have two options for radiation, either discrete transfer or discrete ordinances. Discrete transfer is always included, but you can only really use this if you have very high temperature gradients for something like lamps or furnaces. Basically heat sources higher than 1000 degrees Kelvin. Not common and definitely not used on electronic devices. So, if I did have the HVAC package, then I would switch this over to discrete ordinances. This one can handle low temperatures like electronics cooling. If I did leave discrete transfer on, I would probably have overly averaged heat throughout my circuit board, and the temperatures overall would probably be a little bit higher. So if I had a choice, I would choose discrete ordinances, but if you don't have that package, leave this off. Turn on gravity because you need gravity for heat to be rising inside the simulation. Otherwise, it just sort of expands outwards in a strange bubble. And that's all we need here. We'll have air be our default temperature. I'm going to choose a particular metal to apply to all the different components. If this is the first study that you're going to be running, what I recommend is actually running it with an insulator material. This way, if you accidentally forget to add a material to a component, it's more obvious in the results. You'll just see no temperature distribution on the part file. Okay, we're ready to go. Let's start by importing particular materials. Now we can add a material to each component. However, the quick tip is to just import it from the SOLIDWORKS material library, as long as you do have the correct amount of data. So I'll just import those real quick, not set those up by hand. Alright, next step is to take a look at the heat conditions again. We'll do the volume sources just like before. This time selecting components, same issue. So what are we going to do? We're going to use our select bodies filter. Now we can grab that really easy and get that wattage in there. Alright, same conversation. When you're applying this to multiple components of the same volume, how is it distributing? Same way as it was doing in FEA, it's looking at the volumes and associating the wattage per volume. It's not saying this wattage divided by 4. Alright, we're going to take a small aside and talk about these handful of tools here. These ones are only available in CFD's electronics cooling package. Since I don't need them in this component, I'm still going to talk about them. Let's start with the thermoelectric cooler. Okay, so the thermoelectric cooler is us representing this piece in the middle. Instead of modeling all the different components, you represent this with a cube inside of SOLIDWORKS of the same exact overall shape. And then we have assumptive materials that come downloaded with the electronics cooling package that represent the heat loss across it. You could also, of course, set up your own custom heat loss equation for the thermoelectric cooler. The next type that we have is the 2 resistor component. So what is kind of going on here is we're representing a couple different components by a fully adiabatic system. We have no heat loss through the walls. We're actually simplifying the whole face with single nodes. So instead of having a whole face of say 10 to 20 nodes, we just have a single 1 node. Simplifies the calculation, makes it run a bit faster. It does average the temperature across the entire face because of that. Next up is heat pipes. Heat pipes are a multi-phase system, and we cannot do multi-phase interactions inside of flow simulation. So we represent them in SOLIDWORKS using a simple cylinder with heat transfer from the inside face and the outside face. We assume the fluid movement through the center is so quickly that there's no heat loss through the walls. So if you apply a heat pipe to your cylinder, you're automatically going to have insulated conditions on the outside faces. Okay, next up is thermal joints. Remember how we simplified the model when we were doing configurations? Same concept here, assuming we simplified the model in some way, or perhaps parts are slightly separated because they're going to have glue between them. Use a thermal joint to combine 2 components that have a gap between them. That way you can have heat conduction between the 2 faces. Alright, next up is the PCB calculation. These ones are made up of alternating layers of FR4 and copper. Okay, so as you input this into the table, you're telling it how much of each layer is covered in copper. So this does not have to equal total to 100%. This is talking about 100% per layer. Then what SOLIDWORKS does is combine all of these calculations together and find an overall thermal conductivity and so on across the whole thickness of the PCB. Alright, final thing we have is electronic conditions, most commonly used when we're talking about joule heating. In this case, we could see how much heat is getting produced because of current. What's important to know and remember is to have a high density of elements across wherever you've applied the electrical condition. So I would say 4 to 5 across the diameter of this wire. Okay, you always have to have a goal when you're running a CFD. Now what I want to do is apply a temperature goal. So let me come over here and hit temperature. Hit OK. Okay, I've got to have a volume goal of a particular component. Let me hit OK on that. Still not making any sense. Can't apply it to the body. So what's going on? There are 2 temperature goals in CFD. One's for fluid and one's for solid. What's strange is the solid temperature goal is way at the bottom of the list instead of right here next to the fluid one. A goal is very important. It gives us something to converge on. I would recommend always having goals for data that you are concerned about and want to get out of the CFD. This will make them slightly more accurate than if you were using surface parameters or volume parameters later. Now let's take a look at the mesh. So the way I like to look at meshes is by using cut plots. Now what a cut plot usually does is trace the outside geometry of the part. This makes it look like it meshed everything perfectly. However, it likely did not, especially if this is the generic initial mesh. So what I recommend you do is also look at your mesh using options and then use CAD geometry. Turn that off. This way it's not tracing the outside borders anymore. Now let's take a look at this again with this part hidden. See these strange lines where the vents used to be? That's actually what SOLIDWORKS thinks the vents are. You can see how completely off that is. So what I recommend is creating a sort of a dummy component. That's what we call these. You can make them at the part level, at the assembly level. and then go into your mesh, go to local, or select that dummy body that you created. And then refine the fluid cells through those vent faces. Alright, let's take a look at some of these results. I will start by looking at our cut plot and checking out our mesh. This time, still a little chunky about those vent faces, a little bit better than before. I would definitely refine that maybe 1 or 2 levels further to get the right accuracy through those vent faces. Now for more tips with the results, the first I like to do is when I'm putting in cut plots, we can change the gradation amount in the legend. And I also like to go to streamlines and take a look at the streamlines through here. If you're a little bit more familiar with CFD, you'll know about flow trajectories, which can get you similar information. I personally like the streamlines option because it gets very, very detailed. Now in our cut plots, we have a couple different options than just the normal pressures and velocities. For temperatures in particular, we have things called the bottleneck result and the shortcut result. So for the bottleneck, this is showing us where our high resistance areas are, where our heat is gathering. Shortcut similarly tells us where a lot of heat is passing through, so we could use that for placing cooling lines. Alright, one more type of result I want to show, and it has to do with surface plots. So again, you could click every single surface like we did with convection. To make your life a lot easier, just select the components that you want to get the surfaces for, and then use this button, which selects all the component faces. We'll grab temperature and check this out. Alright, next thing we want to think about is the colors on the legend. The red to blue is nice, but if I was comparing these results with my lab testing, very likely in my lab I was using a heat gun to measure overall temperatures on all the components. Now heat gun colors are not red to blue, instead they are more this black to white through a purple range. So we can get those colors by double clicking on the legend. Let's take a closer look at this. We have some bad resolution on the face of the PCB. This is partially due to the mesh, but no matter what, you're always going to get that kind of chunky look, which is unfortunate. However, this is because this is showing us the heat directly on the face. Even in real life, the heat gun would be measuring heat slightly off the face. So, let's go to our edit definition, go down into your options, and choose to offset it just slightly from the face. That'll get you a more smoother look for a more direct comparison. And that is it for our webinar. Thank you guys so much for tuning in. And again, this has been Shivani with GoEngineer.